Okay, there are people keeping asking to be admitted, but anyway. Right. So before we start, let's just do a few announcements essentially. And well, the first thing is I hope you are able to find the lecture and practical recordings. Right. So there is the announcement on the unit website on where to go to find the lecture recordings for the download. So again, I know that some students just want to download the lectures and then and then watch them disconnected from the internet or whatever. So such an opportunity is, of course, provided. You need to go to the unit website, to the SAT 741 Deakin Cloud unit website. Go to the resources, and you will see there are lectures and practicals for download, and you can watch them there as well. But if you don't need the download facility, you can just go to the Microsoft Teams and watch the recording from there. You cannot download it from there, but you can watch it. Now, note that also that the recordings don't appear immediately or automatically in the unit website. So I need to manually download them and upload them because Microsoft Teams doesn't allow you to download the videos. I don't know if it has changed, but to the best of my knowledge, it hasn't. So that's essentially the story with the recordings of the lectures and of the practicals. Again, the recordings are available. If you see that there is no recording, drop me an email because it may happen that I have just forgot to download it, or you are just looking in the wrong place. Okay. Right. As I have already told you in the last lecture, our SAT 741 is, is the unit which includes the mathematical foundations and statistical foundations of statistical data analysis, which means that it involves some mathematics. And I know that, that some of you may not be confident, right? Or just may have had mathematics very long ago, and you may, well, essentially, you may feel, not confident or just in need to revise the things, right? And there are a number of opportunities provided for that. First of all, I want to tell you a little bit about the Deakin Math Mentors. This is the scheme which runs constantly at Deakin University, and you can either enter Deakin Math Mentors in Google, or you can just follow the link provided in the lecture, which is this one. So you'll click there, and you will see a screen like this, right, with the buttons on the timetable, and there will be literally people, alive people, right, sitting there and waiting for you, and essentially providing you some support, right? So note that they are not tutors or teachers, but they are students which are able to answer the questions and help you also to find those answers, right? So they will be able to help you with mathematical concepts, with the probability theory concepts, and so on and so on. And there is also an email for contact for you to provide. But anyway, so my message to you is that if you are struggling with mathematics, don't think you are alone. right? You can just go to Mathematics Mentors. Of course, you can contact us, I mean, the teaching team for SAT 741, meaning that you can drop an email to me or to Anagi or to Amna, whom you have already met last week, and you know that they are very good and very proficient teachers and professionals, and they know their business really well. Right, and also you should not forget about the Help Hub, but I'll tell you a few more words about that a little bit later. So again, remember about there are a number of schemes and number of layers which are provided to you to support you in mathematics. And again, what we want to remember, I mean, it may not be crucial at particularly this moment, but we want to remember that in the end of this trimester, we will have the end of term online exam, right? And that online exam will include some derivations, mathematical derivations, meaning that you will need to type or write them on a piece of paper and scan, right? Or take a picture of that and submit. So I'm sort of more and more convinced that that the exam will be again online, and it will be it will be like this for long. Yeah. So this is where I'm coming to now. As those of you who are in Melbourne and who had hopes to attend the practical on Wednesday on campus, you you probably have already guessed that that has been cancelled. Now, not the practical has been cancelled. The practical will go on online on the same time. So the practical will be on Wednesday, 6 p.m. on time, but online in the Microsoft Teams. There is already an announcement which I've put today morning about that with the link provided. So if you belong to that group, or if you want to join that group, please do it, and use the resources which you are given. But again, remember that there is no on-campus practical. All those practicals have been moved to online, and I have posted the link to the online practical on the unit website. Okay, right. So now, today is Monday, right? And I haven't released it yet, but we need to be aware that there is the assignment 1, which is coming soon. So the assignment 1 is worth 25% of the final mark, right? It is due on week 6, Friday, 27th of August, 2021, 8 p.m. Now, if you are in a different time zone, drop me an email and I will change your time zone. Well, essentially, I'll just extend your deadline by a few hours. Now, I haven't released the assignment yet. Last year we had our lecture on Thursday, and I had it released. But you can hope to, or you can expect to see it in the next few days. Okay, the assignment. What I do recommend is to start early. What you want to do is you want to download the assignment and to understand its structure. You want to look at it, you want to see what is involved, and so on. So you want to study it, and you want to know what is required, and we already have had the first week practical. So even those of you who have not studied SAT SAT 718 or previously R, you will see that you will be able to start working on this assignment. Well, actually, I need to check what has been copied about the. That's interesting. So yeah, so it may be something different. I think I have fixed. So okay, yeah, you better check those deadlines and yeah, okay, and don't confuse it with the assignment. So again, remember there are quizzes, there are assignments, and there is the final exam. Well, yeah, I know. Right. Okay, so you can go to the Help Hub unit and you will get the Help Hub allocated session, right? So there are Help Hub allocated, there are allocated sessions for SAT 741 in Help Hub. And again, there will be Anagi, I think, who will be sitting, who will be waiting for you and waiting for your questions to come, right? Again, Anagi obviously knows this unit very well, and she will be able to provide you all support which is possible. Okay, so remember that there are math mentors, there is the Help Hub, and remember that the assignment 1 will be released this week, and I will check the deadline, the deadlines. Because I don't think there is anything published on the assignment yet, so you might be just seeing the last year deadlines or something like that, but even that is not correct. Anyway, okay. So today we have an important revision lecture, which is only the first part of the revision we have in this unit, and we are going to talk about the probabilities, and we will review the number of concepts which well, some of you have had already previously in the previous units, and well, maybe some of you haven't yet. So again, this will be the lecture about the probabilities review, right? And in the last lecture, we have already covered, among a few other things, like ethical questions of working with human-related data, right? We have covered the very fundamentals on what the probability is, right? Today, what we will do is we will review the key concepts in the probability theory. So what we will do is we will revisit the concepts of event and the probability of this event to occur or not to occur. We will see that those events are essentially random variables, and the probabilities are described by their distributions. What we will look at also is a number of things around the conditional distributions and independence of random variables. Also, we will look at the, well, centerpiece of the probability theory and statistical data analysis, which is called central limit theorem or central limiting theorem. It's don't confuse it with the big numbers, right? It has nothing really to do with the big numbers, but we'll talk about it later. And also, we will look at something completely different, and we will have a little bit of time for that. We will look at the concept of tidy data, which appears in R, in the programming language we are going to use in this unit. right? Tidy data is again is at the core of R. Essentially, the well statistical methods which are provided by R, they require the data to be tidied before they are applied. And this is what we are going to do. Again, what we are going to look in the lecture, what we are going to do in the practical, and what we will use in the assignment to score those top marks. Right. So again, in the last lecture, what we have seen is essentially the realistic description of the world around us. The world around us is not really deterministic. The world around us is uncertain. Of course, as human beings, we want to reduce this uncertainty. And that's why the whole science of statistics has been introduced or appeared. And the main, like, meta aim, if you want to, right, of statistics is to use some information which is contained in the data, in the measurements we have, to use those to reduce the uncertainty. I mean, well, we see it all the way around us, right? So we see the weather forecasts, and the weather forecasts use the current and the previous data and the statistical models and the physical models to essentially to reduce the uncertainty in the weather forecast for tomorrow. Because I'm sitting here, I'm not the weather forecaster, right? I don't know what the weather will be tomorrow, literally. It can be raining, and it can be snowing, it can be blue sky. What the temperature will be, I have absolutely no idea. But there are those guys who are forecasters. They take the data, the previous observations, apply statistical methods, and provide prediction for tomorrow, which aim is to reduce the uncertainty in, for example, in temperature measurements. Right? Now, what we have already said is that statistics is mathematics. It's a branch of mathematics. So what you need to remember is, again, is the Help Hub, mathematical math mentors, and again, and us if you struggle with mathematics, because we will be covering a number of important mathematical concepts in this unit. What we also looked last week is the data types. And for those of you who are already programmers, and for those of you who know that there are variable types in programming languages, we have already discussed this point that mathematical data types or statistical data types or data science data types, if you want, they are different from variable data types, but they determine the suitable methods for statistical analysis, right? So, well, a label or a nominal data type will, will mean that we will need to use some specific methods of data analysis for this particular data type, right? Metric data type will mean that we need to use specific methods for this particular, for the metric data type, and so. And again, as I have already told you, what we need always to remember is that if we work with human-related data or the data collected from human beings in whatever sense, right, either it's questionnaires or it's medical or health data, what we need to remember is that analysis we do can affect well-being of those human beings. And we need to consider ethical issues of working with that data, right? So we always need to remember about those things. Okay. So in statistics, we work with probabilistic events, right? In other types or branches of mathematics, we work with deterministic events. And those are very different from each other. Essentially, deterministic event allows only for one possible result, right? Think about a formula or an equation. Let's say an equation which determines a salary of employee in a company, right? And that will be an equation which, let's say, the age of the employee multiplied by 1,000 plus the level of education multiplied by 10,000 plus a number of years of service at that particular company multiplied by 5,000, and so on and so on. But this is the formula which is entirely deterministic. It means that you substitute there those values which are also determined, and you get a single value of the salary which is also fully determined. It doesn't allow any other interpretation, or it doesn't have any other value. There is just one single value of the salary for that particular person, right? Now, or yeah, we can think about different way, right? So we can think about the question we ask. So who is the current prime minister? It's very well defined, right? So we know that the current prime minister of Australia is, who was that? Scott Morrison, whosoever, right? And it's very well defined, right? So it's a deterministic event, okay? But on the other hand, our world around is not really that certain, right? And we have a different type of things. And that different type of things is the probabilistic event, which means that the value or the outcome of that can take on a set of possible values, not a single value, but multiple possible values. And again, we can think about who will win the next election, for example, right? And there will be a number of candidates for the prime minister, and we will vote. And again, there is the certain probability which we can find if we do the model of the election, for example. There will be certain probability for one person to win or for another person to win. Sorry, it's just something is happening and I need to quit from here. Yeah. So essentially those probabilistic events, they capture uncertainty and they come from the subset of possible results. And those possible results, they are multiple, right? Again, those probabilistic events, they capture the things we don't know for sure. You can think of, again, those probabilistic events of, or as about a measure of our belief in it, right? Based on some sort of a model or intuition or anything like that. So let's think about it formally, right? We have an event A, for example, in AFL, the Cats will win the grand final, right? Its probability, which is P, which is probability of A, right? Event A, the probability of event A, is a number between 0 and 1, right? 0 means that it's not going to happen for sure. 1 means that it's going to happen for sure. So the intuition behind it is what we usually work with and what we usually live with, right? So let's say that example is the Cats winning the grand final, but there are also alternatives, right? So the Cats can win the grand final, or the Hawks can win the grand final. So the probability of A, P of A, measures how much we believe in A to happen relative to the other possibilities, to the alternatives, right? So we can say that we believe that there is a higher chance for the Cats to win the grand final than the Hawks, right? It means that P of A is greater than P of not A, which is the Hawks. Okay? So we can think again. We can think about the coins. Essentially, well, we are, as we have seen, we are uncertain about the outcome of the event, and this is at the core of the probabilities, right? So we just look at the simplest case, probably, which is the $1 coin. When we throw it, it lands either on heads or on tails. Now, in the case of fair coin, we can predict that the coin will land on heads or on tails equally likely, or the probability for those two events, where one event is the coin landing on heads and the other event is coin landing on tails, are equally likely and are equal to 0.5, right? Now, what is interesting here is that, well, essentially, yeah, we can quantify the risk of alternative decisions. And casinos know it really well, and essentially casinos are built in that way to maximize the profit. So that, well, casinos are very interesting things, in fact. So casinos are made that way that the probability for you to win is low, but it's not low enough to discourage you from going there. Right, so it's a very tricky business, in fact, to rip people off. Yeah, but this is how they make money. Essentially, what they do is they quantify the risks of not winning versus the risk of losing you as a client. Right? And you can already see this is some sort of a multi-dimensional problem. So it's not just the problem of a particular heads or tails coin or a particular game where you can win or you can lose. This is more complicated thing which has multiple parameters in it. And we already think about that there are parameters which are involved, right? And which we can vary as well sometimes. Or alternatively, in the case of COVID-19, for example, those parameters naturally appear due to mutations, right? And as we have seen, this new version of COVID-19 virus is, well, essentially is much more infectious. And this is why we need to rethink the strategies, we need to rethink the methods, we need to recalculate the models and everything, right? Including the proportion of vaccinated people to get into the herd immunity regime. So you can see that there are already sort of parameters involved, right? But what's also important is that we do have a predictive power there, right? So if we think about, again, well, how to tell you? science in general aims at being predictive, right? It's it's very clear when we have the deterministic relationship where E is exactly equal to mc squared, right? So everything is simple here. You just substitute m, substitute c, and calculate the energy, right? That's essentially that's it. And the energy has one single value, and well, we have predicted the energy, which we have calculated the unique value for the energy given the mass and the light speed. In the case of statistics, it's slightly different, right? In the case of statistics, what we have is a probabilistic relation where some random variable x is described as a random distribution. In this particular case, it's Bernoulli distribution, which we'll look at in a few minutes today, right? Of some sort of parameter of 0.5. So you can see, I mean, the parameters are here and there, but the idea is completely different, right? So in the case of deterministic relation, what we get is a single number, which is E, right? In the case of probabilistic relation, what we get is a distribution, which is given by some probability distribution function. So my X can take any value from a list of allowed values with a certain probability. And this is what we call predictive power in statistical models, right? So essentially what we need is to get some sort of a probability and say that, okay, that the event we are looking for is happening with the probability of whatever, 0.3 or something like that, right? So this is the main difference between statistics and not statistics. We don't know the exact value when we have probabilistic relationship. What we know is the statistical property of our random variable x. We can find the mean, we can find the variance, we can find many things around there, right? But we will never be able to find the exact value of x. Okay, so a few other things here, right? What we need to essentially to recall is the conditional probabilities, right? So this is P of A given B is equal to P, or the probability of A given B already happened, right, is equal to probability of A and B happening together divided by the probability of B. So, well, we can talk about some sort of an intuition about it, right? And again, we need to think about it in probably in slightly different way than what you have seen before. So let's think about the green and red apples of small and big size, right? And all of them are in a bucket. And we know that, okay, that there is certain distribution in red apples on their size. So there are, let's say, 3 small and 5 big or something like that. And there is also the same distribution on the, or similar distribution on the green apples. Let's say there will be 2 small and 6 big or something like that, okay? Now, what we can do here is a little trick, right? Essentially, what we can do is just by taking the apple and measuring the color of apple, we can already find what the distribution of sizes of those apples are, right? So when we pick the red apple, we know that, okay, that this is the red apple and it has the distribution of 3 to 5 or something like that, 3 small, 5 large. And we can use this information to essentially to improve our predictive power, if we want, right? So we can improve our prediction on what happens next. So if we take the red apple, we already know that the sizes are distributed in such a way as we have learned before, right? If we pick the green one, again, there will be a different distribution. So essentially, using the conditional probabilities, we can improve our forecasting capability or predictive capability or predictive power for the statistical model. And this is at the core of statistical modeling. So what we do essentially is we come from conditional probability to conditional distribution, right? So what we have is, again, is a number of parameters which we put into our statistical model, and we use those number of parameters to reduce uncertainty and to create a better statistical model. Right. Okay, so what we need to do still is we need to sort of introduce some bits and pieces on mathematics, and we need to do it in a mathematical way, essentially starting from the fundamental definitions, right? So we talk about the random variables, right? Random variables can get those values with certain probabilities, right? Same as, well, as with coin, we have head or tail, and if the coin is fair, there is the, well, the value head or tail is the random variable, right? And we can assign the probability to the head or to the tail, or we can assign the probability distribution to that random variable, right? So a random variable is a function which maps events like heads or tails to the values. What we need to do here is this important distinction. There will be discrete random variables and there will be continuous random variables, right? So discrete random variable is what we get when we throw a die, right? So that can, again, the cube has six faces, right? So the outcome of a trial, right, when we throw the die, can be only from a given set of values, right? So for the discrete random variable, the image of the random variable can have only a fixed set of values x1, x2, x3, up to xn, right? In the case of a die, what we do is, or what we have is the image of x in this particular case is 1, 2, 3, 4, 5, or 6, right? And on top of that, since x is the random variable, we don't know which value it will take for sure. But what we can do is we can give the probability for the random variable to be equal to one of those given values, right? So the probability for the random variable is equal to, let's say, 1, when we have 1 dot here, is defined. We know it. If it's a fair die, it will be 1/6, right? The same is for x is equal to 4, right? So we have 4 dots here. It means that xi is x4 is equal to 4. So the probability for our random variable, which describes the behavior of our fair die, is equal to 4, is also equal to 1/6, right? So what we have here is the discrete random variable, and it's called discrete because the outcome of the trial is essentially drawn from a fixed, finite, discrete set of values. Right? In contrast to that, we can have the continuous random variable. Now, if we think about this voltmeter, right, which measures the voltage of a battery or a number of batteries, right? Continuous random variable is the value of the voltage, right? Now, that voltage value is already not drawn from a discrete set of values, right? But it's drawn from the set of real numbers. With the continuous random variable, the probability is defined only for the random variable to be between two values, right? So the probability for the voltage to be between, let's say, 1.4 and 1.6 volt is defined. Think about it this way. You have a big box with 1.5 volt batteries, those AA batteries, right? You take the voltmeter and start measuring the voltage on each of the batteries, right? You will get some values probably from 1.45 to 1.55 volt if they are relatively new. But you will never get an exact value of X, which you, let's say X is equal to 1.5. There will be always 1.5007 or 1.52 or 1.4995 and so on. It will be close probably to 1.5, but it will never be exactly that value. So the probability for continuous random variable to have an exact value is equal to 0. Right? But the probability is defined for the random variable to be between A and B, between two values. So let's say my 95% or P is equal to 95 for my X is in between 1.45 volt and 1.55 volt. It means that 95% of batteries in my box will have the voltage between 1.45 and 1.55 volt. Right? Now, there is a huge difference between those, between discrete and continuous random variables, right? And the difference is essentially in the way how we treat them and how we describe them, right? For continuous random variables, such a thing as probability distribution function, which is PDF, is defined, right? And this probability distribution function is essentially is equal to the derivative of the probability for the random variable to be less than certain value on X, right? And we will look at it again in the next lecture. So if you don't remember what that thing is, we will revise it. It's okay. Don't worry about it too much. Yeah. So there are multiple examples of those continuous random variables. They can be again voltages on batteries, sizes of apples, right? So you cannot have apples in the real world. They will be shaped differently and sized differently as well, but there will be certain again random variable which can be attached to those apples and can be again described as a random variable, right? Yeah. Okay. So the good thing again about R is that it's specifically designed for statistical data analysis, and it means that it can generate those probabilities and the distributions, right? So, well, essentially, it can generate you the random variables of different types, right? So what you need to do is you need to load that library probe, which is the probabilities library, and there will be a function roll die. You will get the one die with 6 sides, and we will generate the space of the outcomes, and this is what your output will be, right? So it will tell you what is the probability for each side to occur, right? So for one, it will be, well, it's 1/6, right? So 0.1666. For two, it's 1/6, and so on and so on. So you can see that the probabilities are equal, and the R simulates the fair die. Right. With the continuous distribution, we will see how to generate it. But again, what we need is two different concepts, which are about the same, which describe the same distribution, or which describe the same random variable. Sorry. But slightly differently. So there are two things. One of them is the cumulative distribution, and the other is the probability density function. Cumulative distribution shows you what is the probability for a random variable to take the value less or equal than certain value. Let's say we have x equals to 1, which is somewhere here, right? And we can see that y is equal to 0.8. It means, or roughly 0.8, it means that, well, probably not 0.8, but 0.9, right? It means that the probability for this random variable to be less than 1 is 0.9, okay? Same as, well, let's say the value of our random variable is -1, and we can see that the probability for the random variable to be less than -1 is equal to 0.1, okay? Now, at some point, of course, it saturates, and all values below 4, or no, not all values below 4, but the random variable, which is described by this cumulative distribution function, will have the probability for its value to be less or equal than 4 equal to 1. And probability for the value to be less than -4 is equal to 0. Okay? Now, the density distribution function, as I have already shown you, is the derivative of the cumulative distribution. Well, it shows you the, well, essentially where the most probable value is, right? So essentially, if we think about, okay, let's think about apples again, right? And we subtracted the mean weight of apple from, no, apples are not good. Let's think about watermelons, because watermelons are big, and we can think about the kilograms here. So we already subtracted the mean weight of watermelon, right? And we have many of those watermelons, and we know that there are no watermelons which are less than 4 kilos from the mean, right? We know there are, let's say, 10% of watermelons with the weight less than 1 kilo from the mean, right? We know that, again, that the most frequent watermelon, which is here, which is 0.5, right? This is the mean value, right? And we know that the there are no watermelons, or no, all watermelons are below the mean plus 4 kilograms. Okay. Now, using the density distribution function, we can do a different trick, right? We can say that, okay, that how many watermelons fall in the range from -1 kilo to +1 kilo from the mean, right? And this is our interval. And what we need to do is we need to integrate or find the area under this part of the curve, right? And it will be probably something like 0.7 or something like that, right? So 70% of watermelons will fall within the ±1 kilogram from the mean weight of watermelon. So you can see what the cumulative distribution function and density distribution function describe, right? Well, with the case of watermelons, but again, it will be everywhere. And essentially, what we see here is the bell shape of the density function, and the bell shape of the density function indicates that this is the normal distribution, and we will see that normal distributions are central in statistics, and not only in statistics, but in the world around us as well. Okay, now, can you tell me, just to wake you up there, what is the difference between probability and distribution? We sort of looked at it already when we were thinking about the watermelons. Type your answers and suggestions in the chat box. So what is the difference between the probability and the distribution? Not exactly. Yeah, but I mean, Alex, you are very close. Yeah. Exactly. Yeah. So essentially, yeah, exactly. So you are right. You are very correct there. You are very correct. Essentially, probability is applicable to a single event, right? And the distribution is the function. Exactly. So think about those watermelons, right? We take one watermelon out of many watermelons, and we know that the probability for watermelon to have that weight of -1 kilogram from the mean is, well, 0.1, right? So the probability for that watermelon to be below 1 kilo from the mean, below below 1 kilo from the mean is 0.1. There is one single value, right? Now, the distribution, however, describes the ensemble as the whole, because we have many those watermelons, right? We have lots of watermelons. Each of watermelons has its weight, but this is the distribution shows how many watermelons are distributed. Yeah. So again, probability is a single value. Distribution is a function. Okay. Right. Should we have just 5-minute break? I suggest, right? To, I don't know, to do whatever we want to do. But the next part of the lecture is essentially is about a few types of discrete and continuous random distributions, and then we will also look at few more things. Okay, so let's just have 5-minute break, and I'll get a cup of water. I forgot to mention one thing here, but let's just wait one more minute probably. How are you doing there? Those who are in Melbourne, yeah, well. It's yes, yes. It's interesting that that we don't know in this case when our lockdown will end. Yeah, exactly. I don't know. I somehow am quite lowered at this year. I mean the work duties in general. So I literally don't feel too much difference. I wake up, put myself in front of the computer, and then sit for the whole day until like 6 or 7 p.m. and then then I detach or unstick from from my computer, and then this repeats. And it won't be any different if there was no lockdown or whatever. Right, but oh, right. So there are also people from New South Wales, which is yeah, exactly. Yeah. Well, anyway, so I just forgot to mention one thing here that we will look at it again next lecture and the lecture after, I think. But what we want to hear at this point already is that. Cumulative distribution function and density distribution function are connected, right? So the cumulative distribution function is an integral of density distribution function. And the density distribution function is the derivative of the cumulative distribution function, right? So that's what we need to remember and what we start. Yeah, exactly. Yeah. Only yeah, but it's good. Christmas is coming, right? 3 more lockdowns and we are there. Yeah. Okay. So let's look at those few distributions. Now, for the discrete variables, so again, we remember we talked about the probability distribution function or probability density function. I mean, normally it's called probability density function, right? But sometimes it's probability distribution function as well. But for discrete variables, we have the probability mass function. Essentially, if you think about it, so why it is called the mass function, it's because everything is concentrated at that particular discrete value, right? So the probability is sort of squeezed into that discrete value, while in the continuous variables, it's spread around or all over the possible values, right? So we talk about the density because we have, well, here the density, or okay, let's just move back to, yeah. So here the density is higher, which means that there will be an interval for which the probability is greater than here, for example, right? But in the case of the discrete variables, the probabilities are concentrated in those values which are like 0 and 1 and so on. Now, we start here looking at the discrete distributions from the first one, the very simplest one, and probably the most fundamental one, distribution, because this particular distribution has, well, essentially has the applicability like everywhere, right? Including, being crucial as well for machine learning. In machine learning, we often have those problems which we need Tommy, for which yeah, sure. We just have it shortened. Yeah, exactly, Tommy. That you are right. So that's x capital is equal to x. We just have it sort of more compact notation. Okay. Yeah. So in machine learning, we have those problems when we need to classify the things. For example, two different categories, right? Like small or large, sick or healthy. Well, broken, not broken, right, and so on. So. What was I about? Yeah. So this is again, this is described by Bernoulli distribution, right? So Bernoulli distribution, the simplest example of Bernoulli distribution is exactly is the coin, right? With head or tail. And if the coin is fair, we know that the probability for head is equal to the probability of tail. And essentially, if we talk about the general definition, the Bernoulli distribution describes the probability for the outcome in a single trial, right? So, for example, here we have the coin example where x is equal is not equal, but x is in 0 or 1, right? So 0 is heads, 1 is tails, and then we say that p, which is the parameter of the distribution, what we need to remember is that this is the parameter of the distribution, and for the fair coin, p is equal to 0.5, right? And then we can calculate the probability mass function for x equals to 0 and x equals to 1. And if we substitute the values, we'll get 0.5 and 0.5, which is not surprising, right? If we say that the coin is biased, which means that p is not equal to 0.5, but let's say is equal to 0.6, right? We get the heads or 0, 0.4, and tail 1, 0.6. Again, from this formula. Now, since this is the distribution, which is a crucial thing for machine learning, we will be going back to this distribution quite many times. But what we need to remember is that the logarithm of this distribution is essentially connected to many things, to the information, to the entropy, and to the losses, which we aim to minimize in machine learning models, right? So we need to remember that this is very simple, but very, very fundamental distribution for essentially for everything, for machine learning especially, right? Now, this notation is not because it's a discrete distribution. So essentially, it's a compact notation. We have one single random variable x, right? And we can say that that this is the function of a single variable x. Okay. Right. So the next one we look at is also very important, and this is the binomial distribution. Now, the binomial distribution describes what happens if we have n trials. So for the Bernoulli, we have x trials, one trial, and for the binomial distribution, we have n trials. Right, so think about the coin again, fair coin, and we just throw it 6 times, and the probability let's look at this picture, right? The probability to have x equals to 3, meaning that there will be 3 tails out of 6 attempts or 6 trials, is the highest, right? Because we know that it's a fair coin, and we know that it's 50% or 0.5 probability to land on head or on tail. But also there will be again 2, and there will be 4 tails in our experiment, which consists of 6 trials. And and binomial distribution will give us the probability for the result of experiment with the coin to have 2 tails out of 6 attempts. So n equals to 6, x is equal to 2, right? And we will get something like 0.23, right? Now, for x is equal to 5, meaning that it's 5 tails out of 6 attempts, the probability will be something below 0.1, and so on, right? So the binomial distribution describes us the probability for x successful outcomes out of n trials. And you can see that the functional form here is very close to the Bernoulli distribution. Essentially, this is because the binomial distribution is built on top of Bernoulli distribution, right? We just sum all possible outcomes in the case of Bernoulli distribution for the x trials, x successes out of n trials. Now, do you remember what this symbol is? This one, bracket nx bracket. By the way, can I actually? Yes. So this is the number of combinations unordered of x out of n, right? And you also know that there will be many symbols which describe the same thing. So sometimes it's cxn. No, it's n factorial divided by k factorial n minus k factorial. I can write it here. So you have well, I'll try at least, right? So that n x is equal to n factorial divided by x factorial and in brackets n minus x factorial. So it's one of those important things which appear like almost everywhere, because they are very, very natural, right? You have n objects and you drag x objects out of that, and this will give you the number of combinations. It's also called the binomial coefficient because it describes the binomial coefficients in polynomials like a minus b in power n, and that will describe you the coefficients in there. Yeah, so that's about the Bernoulli and binomial distributions. So I'll switch the pen off. There are more important distributions. And there are more interesting distributions in principle, right? So, I mean, those are like, well, sort of easy to understand, but there are more interesting things. For example, Poisson distribution. Now, Poisson distribution describes the probability for an event to occur in finite time. Right? Now, think about, well, discrete event, of course, right? So think about a soccer match, which is 45 minutes. And, or well, the first part of the soccer match whatsoever, right? And you can think of that as a probability for a team to score number K scores in those 45 minutes. Okay? So this is how the distribution looks like. And this is what is the functional form of that distribution. Okay? What we have here is a parameter lambda. Now, what do you think this parameter lambda is? What is the meaning of this parameter? Well, yes, of course. Jason, you are close. Yeah, of course. So for Poisson distribution, the expectation or the mean of the variable is equal to variance and is equal to the parameter. Yes, but the meaning of it is a little different. So it's indeed it's some sort of the time scale, right? But if you think about the soccer match. No, it's not the interval between. No. It's a yes. Yeah. So essentially, if you think about it like, well, in a general sense, this is indeed the expected number of events in a given interval. And this is, again, if we think about the soccer, this is the parameter of the team, which you want to find out, right? If you want to predict the outcome of the game, of the soccer game. So, of course, this has to be understood in combination with the in connection with the adversarial team, right? So because it's team playing against someone else, some other team. But what you want to know, essentially, to go and bid on the team to win, is this parameter. Once you know this parameter, you can, well, win a lot of money, right? So the critical thing here, which I'm trying to bring you to, is essentially what we need to do in this statistical analysis is to find the parameter of the distribution that fits the data well, right? And then we sort of are successful in building the statistical model. Okay. Right. So that's about the Poisson distribution. Now there are more discrete distributions. So for example, there is the negative binomial distribution, which is essentially the probability, which describes the probability of fails. So it's similar to the binomial distribution, but it describes the probability of fails. Now, what you want to note here is those gammas, right? Those capital gammas. Gammas are called gamma functions, which are very interesting mathematical objects because So you know that factorial is essentially the product of all numbers, including the argument, right? But it works for the integer numbers only. So the factorial of 3 is 3 times 2 times 1. The factorial of 5 is 5 times 4 times 3 times 2 times 1, and so on. And it gives you some value, but gamma function is essentially an extension of factorial function to the set of real numbers. So it fills the gaps between the real numbers, and of course, on the integer numbers, it's exactly equal to the factorial, right? Now, the interesting thing about this distribution is that it's more flexible because it has two different parameters. It has lambda and theta, and you can see that the shape of it is sort of close to the Poisson distribution, but since it has two parameters, it's more flexible, and it can fit more data, and essentially it can be more useful, right? But again, there are many more discrete distributions which we are not really touching here. But we want to remember about the main discrete distributions. Okay, so for continuous distributions, probably the most important one is by far the most important one is the normal distribution, which you all probably have seen, right? So the normal distribution has two parameters, mu and sigma, where mu is the mean and sigma is the standard deviation. And just to have some sort of an intuition of how it looks like, of course, it's that famous bell shape, right? And mu, which is the mean, which is the center, describes where the center of the distribution is, right? So for the blue one, mu is equal to 0. For the red one, mu is equal to 0. For the orange one, mu is equal to 0. But for the green one, mu is equal to 2. And the standard deviation is the width of the distribution, right? So the larger the standard deviation, the broader the bell curve is. So you can see that for the orange curve, sigma squared is equal to 5, and this has really, really wide and broad wings. Now, normal distributions are, again, everywhere, starting from the behavior of the molecules in the gases, and ending ending with the galaxies and the world around, probably, right? Because there will be some sort of a distribution of the mean size, and we will see why in a few minutes. Now, what we will use later is this important fact that the second derivative of the logarithm of this distribution is equal to 1 over sigma squared. And this can be easily shown, and we will show this as well in one of the next lectures, as far as I remember, when we will be revising the derivatives and so on. Now, there are many more continuous distributions, and one of them is the beta distribution. It has two parameters, and it's also bell-shaped, but you can see that it's much more flexible. It can be skewed to the left, skewed to the right, and it can be symmetric. And again, it will given the parameters, it will be closer and closer to the normal distribution. again, there are many more continuous distributions. But as I have already told you, the important part of the of statistical analysis, or maybe the first part of the statistical analysis, is to find the appropriate distribution. So essentially, what we do to have some sort of ability to predict or to forecast, we need to find the distribution for the data we already have. And the main thing here is, of course, to exclude the ones which don't fit at all, right? Meaning, for example, well, if we think about the distribution of weights of humans, the weights cannot be negative, right? It means that, for example, that normal distribution cannot work. We need to do something different, right? Or if we, I mean, what can be the other example? Or, for example, if we have heavily skewed data with a lot of positive outliers, it means that we cannot use the symmetric distribution like this one, right? And we need to use something skewed like this, right? With outliers there and with this sort of center of distribution somewhere here. So what we need to think about here is the physical reasons maybe, or, well, our understanding of the data, what can and what cannot be done with this particular distribution in connection to this particular data. So what we need is to exclude the inappropriate distributions. Now, the step number 2 is a little bit more finicky here, because what we do is we select a convenient one. Essentially, we select the distribution which fits the data best and which still is sufficiently simple for us to analyze, right? And again, there is the famous saying that all models are wrong, but some are useful. So what we need to keep in mind is that, well, there is a problem of overfitting, which will come in few months. But again, what we need to have in the model is certain level of simplicity, first of all, and certain level of predictive power. So let's just look at it in a little bit more detail. First of all, we have different data types, right? We have those continuous variables, which means that we need to use the continuous distribution functions. We have those count variables, which perhaps need to use discrete distributions, or we have the categorical, again, which means that we need to use some sort of discrete distribution, or perhaps Bernoulli distribution if the categorical data is just true-false type data, right? Now, what we also want to look at is the shape. As I have already told you, right, if there are many outliers, it means that, well, that those outliers can mean something. And that means that the distribution has to be selected appropriately. For example, if we have that, you know, that long tail to the positive numbers, we may consider to use log normal distribution, which we will see later, right? And log normal distribution does a beautiful thing of bringing those outliers in and essentially putting them under that standard bell shape. But of course, there are quantitative questions we may ask the data, right? So, for example, does mean equal to the variance, right? And mean is equal to the variance for the normal sorry, of course it doesn't equal to the variance for the normal distribution, but it's equal for the Poisson distribution, right? Yeah. And Yeah, and we again, so if we see this, we can already consider the Poisson type distribution, right? And again, what we think of is, well, the nature of the data, right? Where the data comes from and what are the, well, the settings and the circumstances under which the data has been produced and acquired as well, right? So there are also those assumptions which we are willing to make the problem simpler. So for example, we can think about the data which is, well, somewhat different from Poisson distribution, right? For which the mean is not exactly equal to the variance, but it's sort of close, and we know Poisson distribution well, and we know that this will be useful, right? So we always need to think between the balance, or about the balance of between being like completely physically wrong because we assumed something completely incorrect about our data. But on the other side of the things here is essentially is the risk of not reaching a conclusion which can be used. And we need to think about it. There is a very interesting thing which I also want to mention is essentially the maximum entropy principle. Have you heard the word entropy? You can type what you think or what you know about the entropy in the chat box. Yeah. So well, essentially, yeah. So in physics, it's the amount of disorder, but we need to think about the amount of information we have in the data, and well. Um, Essentially, the bigger the entropy, the more information there is. But what we need to think about again is the distribution which we fit to the data, right? And the distribution which we fit to the data should not have smaller entropy, or if you will, variance. The width of that curve should not have the narrower distribution than the data itself. Because those values which are somewhere far, they may be critical for understanding the data and for making the statistical conclusions. Right? So what we want to remember is that essentially the width of the distribution which we are trying to fit to the data should be at least, or well, should be roughly the same as the width of the distribution in the data. Okay? Because this has relationship to the information which is contained in the data, and if we use the distribution which has smaller information capability or smaller entropy, we will potentially miss something. Okay, so what do you think about this? Let's say this is the sepal width, right? And this is the count. This is the famous data set about some sort of plants or something like that. It's like in every statistical software it's included, and it's used for testing purposes. So what do you think about this distribution, right? What can you fit there? Yeah, yeah. So you can fit a normal distribution here, right? Because essentially the width is a continuous, or beta even better, exactly. Yeah, that's correct. Beta is even better because beta is always positive, right? And this is the sepal width which cannot be negative. Yeah. Very good. Yeah. And indeed there can be some sort of a skew here, right? So there are outliers out there. Yeah, exactly. Yeah. Yeah. So we can do this, right? So we can already see from the data that, okay, that this is the continuous value, and we need some sort of a continuous distribution here, and we start thinking normal, maybe not normal, but this is width. So we can fit normal in principle, but normal allows for the negative values, although it will be very, very far and very, very improbable. And again, we can see that there is some sort of a skew and some sort of outliers. And we, in principle, we can think exactly as Jason said, we can think about the beta distribution, or perhaps a log normal distribution again, but we haven't looked at log normal distribution here, right? Now, what we can do again is we can test then those assumptions well, not even assumptions, but we can test how the distribution we have chosen, right, fits to the data, and we can do it with, for example, with quantile plot. Now, quantile plot shows the well, how many data is below a certain given value, right? And we compare two distributions here. So we take, let's say, normal distribution, or as Jason suggested, beta distribution. In this case, it's just normal distribution, right? And we compare this with the data, right? So the horizontal axis is the theoretical quantile, the vertical axis is the sample or the actual data quantile. And we can see that it's sort of close there in the center, right? But it sort of deviates for the higher values and slightly also deviates for the lower values. And indeed, this is what we see here, right? So we see those few sort of outliers which shift our curve or QQ plot up here in this direction, right? And again, there is a very nice capability of R to plot those QQ plots, and we will look at those in the practicals. Don't worry about this too much, right? So we will be doing all those plots in the practicals, and you will understand all the details about what is going on in this in this line. Right, but again, the idea of QQ plot is to compare two distributions. So you choose some sort of theoretical distribution and you have your data, right? And when you plot, there is this line which your data and your theoretical distribution will be lying on if the fit is perfect. But in this case, there is a deviation for the higher values. As we have already seen, there is some sort of a skew here, right? Okay, well, we are sort of late. Yeah, right. So we will need to rush through the things which, yeah. Again, we need to recall the things about the joint and marginal distribution, right? So we usually have multiple random variables, and then we can have the joint distribution, meaning that, okay, that something happening together with something, right? Now, when we know the joint distribution on two variables, x and y, right? We can calculate the marginal distributions from this, integrating it over the variables, right? So to get the distribution on x from the joint distribution, we need to get rid of the variable y. So we just sum all y values together. Okay, and the same applies for the y. So if we want to find the marginal distribution on the variable y, we need to sum all x variables together, right? And you can think about the intuitive example or something like that when you have two random variables. Conditional distribution is what we have already looked at, right? So that's y given x, and x is sort of fixed, and this is the filtering operation, or similar to filtering operation in tie-diverse R, which we are looking at in this unit. Now, in this, essentially, in the conditional distributions is the key idea of statistics and machine learning and statistical analysis. Essentially, what we do is we throw in information and we cut the parts of the distribution which are, let's say, not likely, right? And this is essentially, this is what we are doing here with the conditional distribution, because we put in those conditions. Again, we can plot many things with R, right? And there are many ways of plotting the things in R. So there are those nice violin plots which show you the distributions as well, or the distribution shapes. So it's not only like the the standard box plots, right? But you can have more information in it. And this is, again, this is the example for the sepal widths. What we want to know, or what we want to recall, and what we don't want to confuse with the chain rule for partial derivatives, although it looks similar, we can use the chain rule of joint distribution, right? So those are the products of the probabilities. And essentially, if we just come from the conditional distribution definition in here, we can include multiple variables, and all those multiple variables will be just multiplied, right? And this is also known as the product rule for the probabilities. Well, independence is a critical thing here. So let's say think about the independence of two variables as a simple example of COVID-19, right? So what we have is two different measures which every one of us can do: social distancing and masks. They are independent. Each of them reduces the probability to get infected. Let's say masks reduce the probability to get infected by the factor of 0.3, and social distancing reduces the probability to get infected by 0.1, right? Now, what we do is, again, we multiply those two variables to get the probability not to get infected when we apply both masks and the social distancing, and we get some strange and very small number of 0.03. So you see that, again, that probabilistic approach here is very interesting, right? Now, what we need to remember is that not all variables are independent, as in this case, right? Because there are some also variables which can be dependent on each other, and that means that there is an information in one variable about the other variable, right? And this makes the things more complicated. Now, what we want to also to revisit is, or revisit the concept of correlation. Essentially, correlation is the linear summary of dependence which comes out as a single number. Independence means the correlation coefficient, or the Pearson correlation coefficient, is equal to 0. And this is the definition of the Pearson correlation coefficient. Now, what we want to remember that zero correlation does not mean independence. It means there is no linear dependence, but there still can be dependence which is more complex. This is the beautiful picture from the Wikipedia. Here we have linear relationships which show the correlation coefficients of 1. Or if we have some scatter, you can see that the correlation coefficient decreases from 1 to 0.4 or almost 0 when there is no recognizable line anymore. But what we want to remember is the bottom row here. Clearly, there is a dependence of y on x, but there is exactly zero linear correlation here, because the dependence is not linear. So we need to remember that Pearson correlation coefficient is only about linear relationships. If the Pearson correlation is 0, it does not mean that there is no dependence. It means that there is no linear dependence, right? Okay. Again, you can introduce an additional parameter there, right? And you can say that two random variables x and y are conditionally independent given z if they can be essentially, if they can be decomposed into a straight product of distribution functions, right? And again, when we do that regression analysis, what we need to remember is, of course, the dependency between two variables, and we check the correlation between the residuals, and we will see there is the practical on that. We will do a number of experiments about such a thing, right? Now, there is one critical thing about all this, which is called IID. IID is the independent and identically distributed variables. And this is a critical assumption for the most statistical methods. The problems, of course, come when the things are dependent or distributed in a very different ways, right? So this is the assumption which we normally make about the data, or which we normally prepare the data to fall in, right? So essentially what we want to cross out is the data to be dependent on itself. For example, the past can inform the future. Now, okay, there is a very simple question. In machine learning, can we use random shuffle, train, test splits if data are not IID? And the answer is, of course, it's not a good idea, right? Because essentially, because what we will have is the different properties or different statistical properties of data in different parts of the data sets. And what we want to remember is to pay extra attention to time series data, because again, because the things are interdependent there. Right, and one more crucial piece of information is the central limit theorem. So I'm quite late already, but we are finishing. Now, the central limit theorem is, well, essentially it says that if we have a population and if we drag samples and calculate the means of the samples and plot those means as the distribution will be normal or Gaussian. This is essentially the central limit theorem. Whatever the distribution, whatever the original distribution in the population is, if we take a sample of it or out of it, calculate the mean, put it in the collection, and then make the distribution of those means will be always normally distributed. This is what we need to remember, and there are a number of questions about that in the exam as well. So again, the central limit theorem says that the mean of samples of however distributed population is always normally distributed. Okay? You can play with it, and you can essentially, you can demonstrate it yourself. Just, well, you can go to this website where you can just enter the different things and see how it works. Or you can just take, for example, uniform distribution in R, start dragging samples out of it, right? So you create 10,000 records which are drawn from the uniform distribution. You take 100 size sample out of it, calculate the mean. Take another sample, calculate the mean. Another sample, calculate the mean. And then plot the distribution function of those means. And you will see that despite the original distribution is uniform, the distribution of the means will have the bell shape. Okay? Right. There is one more thing. That's a huge lecture. There is one more thing which you will look in the practicals as well. And the concept there is of tidy data. Essentially, what R wants to is to have the data to be tidied before we start that, understanding part. So your program normally imports the data from somewhere, takes the data set, then there is this tidying step. And then we look at what the data is. So we analyze, we transform, visualize, create statistical models, and then we communicate. Tidy data is a well-structured data, and there are 4 rules for tidy data. The first one is each value must have its own cell. The second one is each variable forms a column. Each observation or record forms a row. And each type of observational unit, a separate observational unit, forms a table. Everything else is called messy data. Right, so let's look at the examples. Again, so let's skip this. Let's look at the examples. Is this data messy or tidy? What do you think? So, yeah, that's right. So, each variable has each column, its own column, single value per cell, right? And different data records are in different rows. How about this one? This one is not tidy, actually. Yes, exactly. Brilliant, Scott. So the type mixed, yes. So what we have is type, which is cases population, and those are 2 different data, right? And we don't need to do it this unpleasant way. We can just add one more column here, and everything is fine. Everything will become fine in this case, right? That's because there are cases and population which are 2 different things here. And again, one row doesn't have one data record because these 2 rows are essentially the single data record. You can do on pivot, yes. We will look at it. So, is this one messy or tidy? Yes, it is. Right, I mean, who on earth does like that? I don't know. But yeah, so those columns for years is not a good thing, right? Absolutely. Okay, right. So we seriously need to wrap it up. I'm sorry for taking it a little bit longer, and yeah. But anyway, we will be looking at the concepts which we have just outlined in this lecture many more times in this unit. So what we have looked at is different types of probability distributions, which are fundamental things in statistical analysis. We also looked at a number of properties for those probability distributions. And we were thinking about, again, about statistical modeling, what is better, what is worse, and we were looking at different possibilities. And essentially, when we looked at the distribution function for the petal widths, we have already done a simplest statistical model, right? And you have suggested that that there can be the beta distribution used in there, right? Now we also have looked at the very important concept of independent and identically distributed random variables, right? But we need to remember that it can be inappropriate to assume IID. We looked quickly, though, at the central limiting theorem, right? And we will need to remember what that thing is because there will be a number of questions around it. And also we looked at the tidy data, but again, tidying the data will be covered in the practicals in a great detail. So we will use, yeah, there is a little remark about that. We will use the old versions of those reshuffling commands in R. However, we will make a note about what to use in the more modern versions. Okay, so I will provide you more information on that in the due course. Okay, so that was it, right? And we sort of, yeah, we are quite late already. But let's say we have a minute for questions, and all other questions go to email. What do you think? I mean, some of you have already learned that I reply emails very quickly, so yeah. So please go ahead if you have last chance. Tidy data rules. Yes, sure. Yeah. So this one. But again, the recording will be provided, and so I just remind you one thing about the recordings, right? You can watch the recordings in Teams, but to download it, you need to go to the unit website. So the first derivative, sorry, the second derivative of logarithm of the normal distribution function, we will look at it, and so I think it's the next lecture, right? So we will literally look at the things like how to calculate those derivatives and so on. There is a little overview of calculus I provide in one of the lectures. I think it's the next one. Okay, but what you do is you just take the logarithm of the normal distribution. The exponent disappears, right? And then you differentiate it twice. should we always take out the duplicates in our data for this subject? You mean for this particular unit? I don't remember if there will be duplicates in the data sets we will be working with. I don't think so. Right? So yeah. But yeah, duplicates are removed. Thank you. Yep. Yes, and you probably want to expect the assignment to be released in a few days before Friday. Before Friday, definitely. Okay, thank you.